Very good evening to everyone present in today's session. Welcome to day 3 of the bootcamp. So, in today's session, we'll be looking at foundation to lithium-ion testing. Okay, so we'll be looking at what are the different testing standards. Okay, what are the different tests that are performed on lithium-ion cells and batteries. Okay, so we'll also be looking at what is the definition of cell testing and what is the requirement, why exactly we do cell testing, and what we gain from cell testing, what are the different tests, and finally, what is the future scope after testing, what exactly is it that is done. Okay, so with that, we can take a look at today's course content. So we start with introduction to cell testing. So as I said, what exactly is cell testing and the need for cell testing. So why exactly it is needed. Okay, and we'll take a brief look at the cell data sheet. So there are different manufacturers provide different data sheets, and whatever testing is done as per the data sheet that has been provided by the manufacturer. And then we'll take a look at three important testing methods, okay, or the other three important testing protocols. Okay, so the first and foremost one is called as performance test, where it talks about its performance with respect to current or voltage, power, energy, capacity, things like those. Then we'll take a look at physical tests or physical abuse tests, basically where the cell is subjected to damaging environments or harsh environments, abusive environments, okay, or extremely hot, extremely cold, extremely wet environments, things like those. And then finally, one is called as life cycle test, basically also called as endurance test. Okay, that is also called as endurance test. So basically, it's a test that done to see what will be your expected lifetime of a cell and expected lifetime of a battery, and for how many cycles and for how many years it can last in the market. Okay, so these are the three important testing protocols or methods we'll be looking at. Okay, then we'll take a brief look at cell testing standards. Okay, so basically we have different standards. We have ISO standard, right? We have UL, we have IEC, we have SAE. So we have so many different standards. So we'll just take a quick look at what are the different standards. And then here at Decibels Lab, we have a certain testing equipment, and we'll just take a brief look at what are the different testing equipments that can be used. Okay, and then we'll have a final overview with future scope. Okay, so once we perform the test, what then? Okay, so that is today's course content. So let's get started with the first topic. So what exactly is cell testing? Let's have a brief look. Okay, so cells and batteries in general, wherever it is you're using them. So it's not just EVs, or it's not just electric cars as such, but in any application, in battery, in mobile phones, in laptops, or in any portable device, wherever it is, even in automobile applications, aircraft, so wherever it is, they so these kind of cells and batteries can experience a variety of different environments and situations, right? So, and those kind of situations could involve things such as different performance situations, reliability issues, safety issues, and different points where they could fail, right? So these are the different kinds of situations that they could face, right? And by subjecting this particular set of cells or a battery pack to these kind of different situations, we're able to understand what exactly is its performance, how is it able to withstand all of this, how is it able to face this, and whether there'll be any such reliability or safety issues, and how it can be modified as per the requirement. Okay, so these kind of situations, or this kind of variation in situations, operating conditions could be as follows, like where you have different ambient temperatures, right? Especially when you try to see batteries being used in marine applications, right? So there it faces a variety of different ambient temperatures. So all the way from very, very cold temperatures to very hot temperatures, or even different humidity, or so very large amount of water, right? Different pressures. The cell and the battery pack could face all of this, right? So even in terms of electric vehicles, different ambient temperatures. So for example, let's say you're trying to operate an EV somewhere down here in the south, in like say Chennai, or say for example somewhere in Karnataka, right? So our temperatures down here are completely different from the temperatures up in the north. So especially in Himalayas, where it's almost always cold, right? So even same thing with the pressure. So uh, altitude variations. So pressures can also come with altitude variations. Okay, so even here your moisture content comes into picture, which is given by different humidity. So your battery packs could face different water content in the environment, right? It could also face physical disturbances such as vibration, impact, thermal shock, cracking, damages, denting, electrical malfunctions such as short circuit, overcurrent, over voltage. It could face all of this, right? So also it could face overcharging and over discharging. So let's say that let's say that you have kept your battery for charging at very high rates, right? So how could that affect the battery? How could it affect the performance of the battery, its temperature, its overall performance, right? And also dewing and condensation. So basically, it's a much more extreme version of humid environment. So dewing and condensation can also fall under the category of submerging test. Okay, submersion, where battery packs can undergo like a severe submerging. It can be submerged under a large amount of water, right? So these could be all the potential different factors that a battery pack could face in real life, a cell and a battery pack could face in real life. Okay, so even including more advanced problems such as failure of protection systems, where your battery management system suddenly starts to malfunction. It's not able to prevent the cell or the battery pack from staying within the current and voltage limits, or within the power limits, or even within the temperature limits. So it could start to overheat, it could even catch fire, right? So all these are the different situations that a particular battery could face, right? So and when you test a cell or a battery with all of these different scenarios in different situations, you're able to get a good idea how it can behave in all of these diverse conditions. Yeah, so that is what is cell testing in a nutshell. So this is how briefly you can explain cell testing. Okay. So with that, we'll now proceed to the need for cell testing. Yeah. So keeping all of the points that we saw in the previous slide, we can now extend this to the need for cell testing. So therefore, by performing cell testing, the idea that we get is, you can summarize it as follows. Okay. So the most important thing you can understand is the limits of operation. Okay. So your limits of operation could be in terms of voltage, in terms of current, power, energy, capacity, state of charge, state of discharge, rate of charge, and also things such as temperature, energy, and also varying atmospheric conditions. Okay, so your limits of operation could be in terms of all of this. Okay, so there could be even more things, but these are many of the commonly listed limits of operation. Okay, so by performing cell testing, you're able to understand what are these limiting factors and how they affect the performance. Okay, so you're also able to understand the real life characteristics and behavior of the cell in and the battery pack. So not only in terms of one individual cell, but also in a group of cell, which is called as module, and a pack level also called as a battery pack. Okay, so it's like a couple of cells, a group of cells make up one module, a group of module makes up one battery pack. Okay, so you're able to understand the real life characteristics and behavior, so you're able to test it out and understand how it is behaving in real time. Okay, so pretty much you can analyze it as to see how it would perform in real time. Okay, you're also able to understand what are the different failure points and failure modes of the battery pack and of the cell, and accordingly design for failure. Okay, so design for failure is a very important aspect. So you're able to understand at what point can the battery pack potentially fail, and also accordingly devise necessary safety devices and algorithms to prevent such failures, or at least to increase the margin for failure. Okay, so for this this is exactly what cell testing helps us in understanding. Okay, we are also able to predict and analyze cell aging characteristics. So we're able to develop algorithms and programs which help us predict to what extent cells can age, how they age, why they age, and how exactly different situations such as cycle life cycle. So a cycle life, or one cycle, is basically one charge and one discharge. Okay, so that is basically your one cycle. And if you were to run your cell through or your battery pack through multiple cycles, then how exactly will that affect the aging characteristics? How will that affect the health, its performance, its voltage, its all of its operating parameters as such? Yeah. So you can only predict it and you can only analyze it, but you cannot give an exact number as to say this is how it would be. But a good amount of prediction can be performed. Yeah. You're also able to understand the performance by physical damage, shocking, impacts, vibrations, overheating, underheating, and things like these. Okay. And when you combine all of this, finally, you're able to analyze all of the information and data processed from these points. And finally, you're able to modify the performance and behavior of the cell to get maximum operational life and efficiency. Okay. So this is the need for cell testing. This is why cell testing is done. Okay. So in a brief picture, this is what need for cell testing is. Okay. So now let's have a quick look at the cell data sheet. Okay. And this is of a lithium ion 2.6 amp hour lithium ion cell. Okay. So that's 2600 mAh. And the specifications are as follows. So starting with the first one, so we have something called as nominal capacity. Okay, so nominal capacity is the capacity you will theoretically obtain if you were to discharge the cell at 0.2 C. Okay, so 0.2 C, or basically the C rate, is the ratio of current drawn with respect to its capacity. Okay, so if I was to discharge a cell at 0.2 C, so what that means is if I were to discharge the cell at 0.52 amps as per the specifications, then ideally you would get a capacity of 2600 mAh with a minimal capacity of 2550 mAh. Okay, so if you were to perform this kind of a test by discharging it at 0.2 C, or as they have mentioned here at 0.52 amps, then you should get a minimum of 2550 and a rated capacity of 2600 mAh. Okay, so this is what the first and foremost point here stands for. Okay, and this is usually rated at room temperature 25 degrees Celsius. Okay, so of course at different temperatures you will have different nominal capacities. It's not going to be the same at different temperatures. Okay, so we will take a look at that in the upcoming slides. Right, so there's the next one, next terminology given over here. It's called nominal voltage. So nominal voltage can be defined as the voltage of the cell at exactly 50% charge. Okay, so if you were to consider the battery or the cell at exactly 50%, 50%, right? So that voltage reading is what is called as nominal voltage. Okay, or otherwise you can also say it is the average reading of the voltage throughout the operation of the cell. Okay, so we know that cell starts at a particular voltage and then ends at a particular voltage during the operation. And if you were to take the average of all of this, it would give you the nominal voltage. Okay, and immediately you can say this 3.7 volts corresponds to a lithium ion cell. Yeah. So following that, we have internal impedance. So internal impedance is basically the sum of all of the resistances that is present within the cell. So you have many different types of resistances that occur within the cell. Okay, so mostly they're chemical type resistances due to reactions and as such. And this value that you see here is the value corresponding to that a particular set of resistances put together. Okay. Then we have discharge cutoff voltage. So discharge cutoff voltage is the least voltage or the end voltage. So also called as end voltage. Okay, it's also called as end voltage. So what that means is below 3 volts, it is not recommended to discharge the cell. Okay, so you can discharge it safely up to 3 volts, and below which, if you were to discharge the cell, it will damage the cell. Okay, so that is what this particular term means. So max charge voltage, the same thing, but except during charging, it is recommended to stay within 4.2 volts and a margin of 0.05 volts. Okay, so standard charge current and rapid charge current. So it is recommended to always follow by any manufacturer. You can take a look at any of the data sheets. They will always recommend to start charge at standard charge current of 0.52 amps or at 0.2 C. Okay, or more generally classified as 0.2C. Okay, it is not advised to charge always at rapid charging current, because this can actually start to wear down the battery pretty quickly. 0.52 will actually give you longer life. Okay, so same thing here with the discharge as well. Next, coming to maximum pulse discharge current. So what this means is, instead of drawing continuous current, it will draw pulses. Okay, so let's take this to be time and let's take this to be current. Okay, so if you take a look at the graph, pulse discharge means that you're discharging the cell in pulses. Okay, and as per the manufacturer, the maximum pulse current it can take is 2.6 amps. Okay, usually they would also provide the time rating, so for how many seconds it can usually take. Usually they would mention it as 10 seconds or up to 15 seconds. Okay, but it depends from every manufacturer as to what they prefer. Yeah, so that is with respect to the maximum pulse discharge current. So this is your classified weight. Okay, and 18 millimeter, 65 millimeter height can immediately you can recognize this to be an 18657. Okay, so 18650 is 18 millimeters diameter, 65 height, and O or 0 stands for cylindrical. Okay, so this is your operating temperature or your recommended operating temperature limits. Okay, during charge it is always suggested to be within this temperature limit, and while discharge you have a larger window. Well, that is because if you are charging it, especially if you are charging it from low voltage, it'll face a lot of losses, especially if it is in temperatures below 0 degrees, which is why it is always suggested to keep it within 0 or above 0. Okay, so that is why your operating temperature is mentioned as such. Okay, and then finally we come to storage. So this is something we'll see in the upcoming slides as to exactly what is meant by storage and what it has to do with the performance of the cell. Okay, so storage is basically like if you are storing the cell for in an inactive situation for a very long time, yeah, then you have to specify the temperature limits for it to be stored. Okay, because otherwise your battery can start again facing a lot of losses, especially at lower temperatures. Okay, so this is just a brief overview of all of the cell data provided by the data sheet. Okay, so all your testing and all of your compliances, all of your requirements has to be as per this specifications given by the manufacturer. Okay, so with that, we will now look at what is cell testing requirements. Okay, so as I had explained earlier, that there are so many different standards, right? So mainly or mostly throughout today's session, we'll be usually referring it to ISO standards. Okay, so as per ISO standards, you will see that there are three main categories through which you will have to perform the cell tests. Okay, starting with the performance test, abuse test, and then life cycle or aging test. Okay, so in performance test, you have all of these categories. So static capacity test and energy test at room temperature, and also at different temperatures, at different C rates or at different current magnitudes, pulse power characterization, internal resistance tests, energy efficiency at fast charging and fast discharging. So it also includes fast discharging as well. Okay, and finally, basically cranking power or low temperature cranking. So there is something called as cold cranking, right? So basically this tells you to what extent can the battery provide power given a particular low temperature. Yeah, so that's what this test actually tells you. Then coming to thermal. So thermal, you have humidity and water type tests. You have thermal shock cycling, so where you'll be exposing the particular cell and battery pack to extremely high and extremely low temperatures. Okay, then you have mechanical tests in which you'll be subjecting it to vibration, so severe vibration, low to severe vibration, and then mechanical shock. So mechanical shock can include light impacts, medium impacts, heavy impacts, accidents, ruptures, cracks, and dents. Okay, and then finally electrical abuse. So you have short circuit, so you can actually simulate both internal and external short circuit and then test it out to see how the battery has performed in that situation. Overcharging and over discharging. So you can see how exactly the cell can behave during fast charge, fast discharge, especially by varying the temperature as well. Okay, so that is both electrical and thermal abuse put together. And then finally, we have life cycle. Okay, so life cycle usually comes first and foremost by isolating the cell in open circuit voltage condition. Okay, or by putting the battery pack in a situation where it is not connected to any load, isolating it for a long period of time, say for example 12 months to over 1 year, 1.5 years, and then seeing how much of the capacity has been lost. Okay, and SOC loss at storage. So SOC loss at storage, that means not only just storage in ambient conditions, but in different temperatures. And then finally, cycle life. So cycle life, as I had mentioned earlier, so if you subject the cell to multiple charging and discharging cycles, so how will that affect the performance? Okay, so all of these are the three different types of categories or protocols that have to be followed. So this is as per ISO. Each standard will have their own requirement, and each standard will have their own definition of what are the different testing requirements. Okay, so in today's session, we will be only looking at the static capacity test at different temperatures, pulse power characterization, thermal shock cycling, vibration, electrical abuse at short circuit, and cycle life test. Okay, so these are the 4 to 5 different tests that we'll be looking at. So with that, let us get started at the first one, that is static capacity test at different C rates. Okay, so basically, as I had explained earlier, C rate equal to the ratio between the current drawn from the cell divided by the capacity, the rated capacity or the nominal capacity of the cell. Okay, so let's just mention that here. So nominal capacity of the cell. Okay, so here this is rated to be 2600 mAh. Okay. Okay, so a C rate of 1 C would correspond to a current of 2.6 amps being drawn from the cell. Okay, and a 0.2 C rate would correspond to a current of 0.52 amps being drawn from the cell. Okay, so I hope this is clear. This is what it means. This is what C rate, which is what is the definition of C rate. Okay, so here on the left hand side, you can see the graph that corresponds to the cell being discharged at different C rates. Okay, so basically this is the testing, or this is the graph that you see when you test one lithium ion cell. Okay, so the same cell that is being subjected to different C rates. Okay, all the way starting from 0.3 C. Okay, so 0.3 C starting at 0.3 and then going all the way up till 2 C. Okay, so these are the different voltage bands or voltage graphs, voltage curves you would notice if you were to subject the cell to such different C rates. Okay, and this difference in capacity that you see at the bottom, this difference in capacity that you see in the bottom is called capacity fading. Okay, and that is the objective to measure, that is the objective in this particular type of test. Okay, so that's one of the objectives. Of course, the main objective here is to see what is the discharge capacity of the cell at room temperature. So again, this is performed at 25 degrees Celsius. Okay, so that is the universally accepted room temperature. So this is the the temperature at which this test was performed. Okay, and at this temperature, these are the different capacities that you would obtain if you were to subject the cell to these many different rates. Okay, so the other objective, of course, is to see to what extent the capacity is being lost at high C rates, especially. So that is what this test tells you. Okay, so the cell is discharged from maximum voltage of 4.2 and ended at a minimum voltage of 2.8 volts. So as per the manufacturer specification, the minimum voltage is 2.8 volts. So that's what the that's where the test has concluded. Okay, so that is static capacity test with respect to C rates at the same temperature, that is constant temperature. Now you can perform the same test static capacity test, but at different temperatures at the same C rate. Okay, so this is the same 2600 mAh cell. Okay, but it is subjected to different temperatures. You can see that here, held at the or performed at the same current rate or C rate. Okay, so that's what this test, that's how this test is performed. Okay, so basically, in order to do this, first and foremost, you have to take the cell and you have to first and foremost expose it to that particular temperature. Okay, say for example, you're trying to test the cell at 30 degrees Celsius. So what you have to do, you have to rest the cell. Okay, rest at 30 degrees Celsius. Okay, you have to rest the cell at 30 degrees Celsius for a period of 24 hours. Okay, this particular time period here is purely dependent on the person who's testing the cell. It is not necessary that you have to do it for 24 hours. You can even do it till 4 hours. You can do it till 8 hours, 10 hours, or even up to 2 days, 3 days, dependent purely on how sensitive you want the results to be. Okay, so but it is recommended, however, that it is kept at 24 hours in order for the cell to obtain thermal equilibrium. Okay, so that the cell achieves something called as thermal equilibrium. Okay, so once the cell has attained thermal equilibrium, then keeping the current or keeping the C rate constant, this cell is discharged. Okay, and here you can see the graph. So your red line over here, this one, it corresponds to your C rate at your C rate of minus 3.3 amps and a temperature of 30 degrees Celsius. Okay, so the same thing is repeated at different temperatures at 40 degrees Celsius, at 10, at 0, and minus 10, minus 20. Okay, so this is actually as per ISO standards once again. So this is the complete temperature range that they have mentioned, right? And the testing is done purely based on these requirements. Okay, so here you can see at lower temperatures, you are noticing that the cell is giving out much lesser capacity, right? So here, especially when you're trying to discharge the cell at like 0 or below 0, you're noticing that the cell does not give you the complete capacity. Well, that is because of the increased internal resistance that the cell faces. Okay, at lower temperature, what happens? The ions that are exchanged. So there are a certain amount of chemical reactions that happen, and those chemical reactions release some ions, okay, which have to be exchanged between the electrodes of the cell. Okay, so these ions will start to lose energy at lower temperature. Okay, and because of that, they will not have enough energy, or they will not have sufficient energy to cross the electrolyte into the other electrode. Okay, so for that purpose, at lower temperatures, the cell faces extremely heavy resistance, and that is why it is not able to sustain itself for a long period of time, and it discharges very quickly, thus giving a very low amount of capacity. Okay, and vice versa for higher temperatures. So in case of higher temperatures, say like 30, 40 degrees Celsius, it gives you capacities beyond 2600 mAh. Okay, so that is why 2600 mAh is always rated at room temperature and not at higher temperatures. Okay, so what this means is that your ions will acquire extra energy, and they will overcome the internal resistance of the cell very quickly, and thereby it is able to give out a temperature capacity greater than 2600 mAh. Okay, so which is actually dangerous. I mean, it may sound good that the cell is giving out such a large amount of capacity, but that is actually not good. It can actually damage the battery. It can start to heat the battery. Okay, where it can then encounter a particular situation called thermal runaway. Okay, so thermal runaway is basically a phenomenon where the cell or the battery pack starts to overheat, and it starts to heat up at such an extent that it's not able to give out the heat. Give out the heat at a sufficiently high rate so that it maintains steady and stable temperature. Okay, so as in when the battery starts to gather more and more heat, your reactions inside the cell start to build up even more, and because of which, at some point in time, your cell can catch fire. Okay, and that process is called thermal runaway. Okay, so that is why it is always preferred to keep the cell up to a maximum of 35 to 40 degrees Celsius and not more than that. Okay. And it is always suggested to keep the cell 0 degrees or at the maximum 10 degrees Celsius. And again, not below that. Okay. So this is static capacity test at different room temperatures, different ambient temperatures at one particular fixed C rate. Okay. So that is what the static capacity test is all. That's what the static capacity test helps you understand. Okay. Now moving on to pulse power characterization. So pulse power characterization is a test basically that is done to perform, that is done so that two things are understood. So the first and foremost important thing is to understand what is called as pulse power of the cell. Okay. So there is something called as pulse power. So basically this pulse power means what is its ability to provide power within a set range of a pulse. Okay. So for example, let's say that the particular battery or particular cell is facing a certain pulse, a sudden pulse. Okay. And to what extent it can provide power without going outside the recommended voltage limit. Okay. So that's what pulse power determines. Okay. It is also called as dynamic performance. So that's the main objective that is the main objective for pulse power characterization. Okay. So it is in order to understand what is its ability to provide power within this pulse period. Okay. Without crossing the performance limits. Okay. So whether it is safe to provide this kind of a pulse, at what pulse does it start to cross the limit? Does this pulse cause short circuiting? All that you can start to understand from this test. Okay. And the second most important thing is you are able to understand the cell's internal resistance and capacitance. You're able to derive these values and you're able to understand what are the different resistances that the cell is facing, and how does the cycle life also affect the polarization and ohmic resistance. So there are two types of resistances that the cell usually gives up. Okay, so the resistances are as follows. So first and foremost is called ohmic resistance. Ohmic resistance. And the second thing, the second type of resistance is called polarization resistance. So let me just clear this out. Okay, it's called polarization. Okay, so I will not go too far in depth into what are these types of resistances and how they occur. You just have to know that mainly because of the material properties and because of the chemical composition, these two resistances can occur. Okay, and by performing this pulse power characterization, you are able to determine accurately what are these two resistances and how exactly they change with respect to number of cycles. Okay, so as and when the cell starts to age, you're able to perform this test multiple times and you're able to get it. You're able to understand how ohmic resistance and polarization resistance can change. Okay, so briefly, you can see what is the type of pulse profile, the current pulse profile that is provided to the cell, and how the voltage response will look like. Okay, so basically what you're seeing here is an entire series of pulses with a series of voltage response. Always this kind of test is performed with multiple types of pulses rather than just one pulse. So, but if you want to see how one pulse looks like, so I can just show that over here. So your x-axis will be in time and your y-axis will be current. Okay, in amps. Okay, so this is the zero line. Okay, and your first pulse will be a discharge pulse. Okay, next will be a charge pulse that will look like this. Okay, and then after which there will be one another discharge pulse. Okay, so there are three such type of pulses that will be supplied to the cell. Okay, so I will write down now what each one implies. So this is a discharge pulse. Okay, this is a charge pulse. Okay, and this is yet again another discharge pulse. Okay, so let's see one by one what each one means over here. So the discharge pulse here, it is meant to discharge the entire cell for 10 seconds, for a period of 10 seconds. Okay. Similarly, you're also going to charge the cell here for 10 seconds. Okay, so this is one set of pulse. So this is one set. So one set includes one discharge, one charge. Okay, so this is basically to see what will be the voltage response both during discharge and during charge. Okay, and now the last one, or the third one, this particular discharge pulse here is to remove 10% of the battery's capacity. Okay, this is to remove permanently 10% of the capacity. Okay, so the battery or the cell is first and foremost started at maximum voltage. Okay, so let's take the maximum voltage of the cell to be 4.2 volts. Okay, so the test is started at 4.2 volts. The discharge pulse is performed, the charge pulse is performed, and then it returns back to its equilibrium, and then one discharge pulse is provided so that it reduces by 10%. Okay, so 4.2 volts is dropped by 10%. Okay, so then starting at 100% charge, it will then be at 90% charge. Okay, it will be at 90% charge. Okay, then again the same profile is repeated, and then once again it is taken down to 80%. Okay, so it is moved from 90% charge to then 80% charge. Okay, then to 70%, so on and so forth till it reaches 10% charge. Okay, it is usually advised to stop at 10%, because at that point the amount of resistance that the cell faces is actually very high. But it can also be part of the experiment where you can take it to 0, but that is sometimes not recommended. Okay, so this is how your entire pulse profile will look like. Okay, and this is what is called as pulse power characterization. Okay, and to this pulse input, the voltage response will look like this. Okay, so this is the 0 line, and yeah, your pulse to discharge will look like this. Okay, so this is what your voltage response will look like, and same thing you'll see even for the charge. Okay, so this is how your discharge and charge pulse, your voltage response will look like. Okay, so this will be your voltage response. Yeah, so this is how your voltage response will look like, and utilizing this voltage response, you'll be able to understand your dynamic performance, or as I said, your pulse power capability. Okay, and finally also you'll be able to estimate your resistances. Okay, so again, I will not be going into the details of how exactly the pulse power is determined or how the cell's resistances are obtained, but using this voltage response, all of that is possible. Okay, so your current magnitude, or the pulse current that you can supply, is usually varied between 0.5 C to 3 C, depending upon what is the machine limit capability, your testing hardware capability, or your cells limitations, and things like those. But usually it is between this limit. Okay, so that is with respect to the pulse power characterization. Yeah. So now that is the end of the performance test that we see. And now we'll see the testing with respect to thermal shock cycling, or abuse test, basically. So physical abuse test, as I had mentioned, we'll be looking at the thermal shock cycling, mechanical vibration, and electrical abuse. Yeah. So as per ISO standards, what they have defined the objective of this kind of thermal shock cycling test to be such that you're taking an entire set of batteries, or entire set of cells, or a battery pack, and subjecting it to a highly thermally stressful environment. Okay, so where the temperature, the ambient temperature changes from -40 to +80 multiple times. Okay, so -40 to 80, and then again 80 to -40, and that is going to occur within 30 minutes. Okay, so this is the set and defined period as per ISO standards, and this is done till 5 cycles are completed. So as I said, -40 to 80 is one cycle, or one thermal cycle, and then 80 to minus 40. Minus 40 to 80 and 80 to minus 40 is one cycle. So yeah, just can make that correction here. So minus 40 to 80 and 80 to 80 degrees to minus 40 degrees is one cycle. Okay, so this is repeated a minimum of 5 times. Okay, so that is as per the ISO standard, and the following things are observed. Okay, so the following things are observed. So the first and foremost thing is, will the battery pack catch fire? Okay, will it catch fire? So as I said, thermal runaway. Second thing, will there be any chemical modification? As in to say, will there be any internal modification to the chemical substances, chemical compounds, the internal structure? Will there be any chemical modification? Okay. Third thing, will there be any vaporization? Okay. So are any of the chemicals or are any of the chemical constituents beginning to vaporize? Okay, this vaporization is also called as gassing. Okay, so this is a phenomenon that many lithium-ion cells face. So gassing is nothing but vaporization of the electrolyte, where basically your electrolyte inside the lithium-ion cell is very volatile. Yeah, so when it is subjected to high temperatures, it can start to vaporize. Okay, also it is called as gassing. So do the groups of cells face this kind of gassing? Okay, and the fourth and foremost thing, is there any loss or if there is any change in mass of the cell? Okay, so is there any change in the mass of the cell, or if there is any loss in the mass of the cell, right? So if all of these are considered, and the answer to, or rather the results to all of this is observed to be a safe result, or basically it is observed that none of these events are occurring, then it is deemed roadworthy. Okay, it is deemed roadworthy. Okay, and these are all what is called as acceptance requirements. Okay, so these are all acceptance requirements. So once all of these, this complete set of tests is performed, then the analysis of all of these is noted, whether if any of these events are occurring, and even if one of these events are occurring, then immediately it is deemed unworthy and it will be rejected. Okay, otherwise it will be roadworthy, and it has then therefore satisfied the acceptance requirements. Okay, so that is the complete set of requirements that one looks at while performing the thermal shock cycling test. Okay, so this is with respect to thermal shock cycling. Okay, there is also something called as thermal endurance test. So this is with respect to short period of time, right? So we have seen that this comes for 30 minutes, but endurance test comes for much longer period of time. So for example, let's say you're subjecting a cell to 50 degrees Celsius or something like that. Okay, for a period of up to 6 hours. Okay, or 8 hours, or sometimes even a period of 12 hours. Okay, so that's what the endurance test does. So it is similar to your thermal shock cycling, except here your cell or battery pack is subjected to a temperature and held at that temperature for a long period of time. Okay, so again, there are several requirements for this type of test as well. Okay, but we will not be going into this. So we are done with thermal abuse tests. Now let's take a look at mechanical abuse tests. So here we see a vibration test bench on the left hand side. Okay, so you can find this complete information on this website here. So Crystal Instruments. So you can, they're like one of the world's leading suppliers of vibration test benches, especially for electric vehicle battery packs. So here what is done? So your battery pack is mounted on top of a test bench, okay, and subjected to a vibration of 200 hertz, okay, in both, in all three X, Y, and Z direction, okay, for a minimum period of 12 hours. Okay, so we know that in electric vehicles, there can be different sources of vibration from the motor, from the chassis, from the wheel, from the suspension, all right, or from within the vehicle itself, from the structure. So all of this is possible. There could be like various different sources of vibration and noise to the battery pack, right? So the objective of this test, this vibration test, is to see how this particular cell or battery would behave if you were to subject it to extremely harsh vibrations. Okay, so 200 hertz is the maximum recommended vibration because of the mass of the battery pack. So not only will it affect the battery pack itself, but even the test bench will be affected. So for that purpose, it is limited to 200 hertz. Okay, and at the end of the test, this particular battery that has been tested will once again have to undergo this set of acceptance requirements. Okay, so no gassing or no vaporization, no leakage of chemicals, no change in mass, no cracking, no denting, no rupture, no external, no internal damage, no fire explosion, or no thermal runaway. Okay, so if all of these are satisfied, then once again it is deemed roadworthy. Okay, so that is the complete objective of the vibration test. Okay, so usually, again, as I said, it is limited to 200 hertz. So now we will look at short circuit test. Okay, so your short circuit test is basically an electrical abuse test. So the purpose of this test is to see what majorly it is to check the functionality of the current protection device. Okay, so all cells and all batteries have something called as a current protection device, or also called as current interrupt device. Okay, so this test is done so that the functionality or the response time of this particular device is checked. Okay, so 55 degrees is the temperature that usually it is kept at. That because, as I said, that is when your cell starts to discharge very heavily or very quickly, right? And that is when your cell is able to provide a large amount of current. So for that purpose, it is kept at 55 degrees Celsius, right? So then what it is done, what is done is this test cell that you see over here, or this test battery pack. You can even mount a battery pack here. It is connected to a low resistance external wire. Okay, so this wire that I'm highlighting here, this is a wire that is of very low resistance. Okay, so usually this would be a wire of resistance less than 0.1 ohms. Okay, so again, this is as per the ISO standards. They recommend to use a wire of resistance 0.1 ohms or lower than that. Okay, so then what has happened? What happens? The cell is then allowed to discharge at very high current rates through the wire, and again, the following acceptance criteria is checked. So whether the cell catches fire, whether the cell is able to sustain itself from without being overheated, whether there is any gassing or venting, whether there is any thermal runaway, right? And if none of these are observed, then the cell is deemed roadworthy, and it is basically accepted in the fact that it can withstand a high amount of abuse. Okay, because this kind of test, this kind of short circuit test is actually very, very rigorous. It is extremely it's quite a difficult test, and usually this is where the battery or the cell would face quite a tough time. Okay, so when the battery or the cell passes this test, it is deemed roadworthy. Okay, so in terms of performance and physical abuse, this is the final type of test. Of course, there are much more in-depth tests, things such as humidity, pressure, altitude test, moisture and condensation type test, humidity tests, and things like partially submerged, fully submerged, and subjected to external fire. So all of these are different tests that can be performed. But this is the one of the final tests that is performed on the cell. Okay, so with that, we come to an end on the physical abuse test. And finally, now we come to the life cycle tech test. Okay, so this kind of test is usually performed after the battery has been implemented, or after the battery pack or cell has been utilized within the application. So whatever application it may be, whether it's a road vehicle, electric vehicle, a phone, a mobile phone, or a laptop, whatever it is, this kind of test is performed usually after the the battery has run a few cycles, or it has elapsed after some time has elapsed. Okay, so this test is simple. There is a storage chamber or a test chamber So which is basically watertight and airtight. Okay, so the cell is kept at 50% state of charge, or basically 50% charge, exactly at 50% it is kept, and it is stored at an ambient temperature of 45 degrees Celsius. It is disconnected from all the loads, again as per ISO standards, and it is stored in this particular chamber for a period of up to 30 days, minimum 30 days. Okay, and after the 30 days has elapsed, this particular battery pack or test piece will be removed from the storage, and once again the static capacity test will be performed at room temperature to check how much capacity has been lost. Okay, so referring back to the static capacity test which I had introduced to you earlier, right, that same test will once again be performed in order to see how much capacity it has lost. Okay, so utilizing that, it can then once again be obtained how much capacity loss has happened. Okay, so this can give you capacity loss. Okay, so loss due to extended storage. So it's not necessary that it has to be only for 30 days. It can be even increased up to a period of 12 months. Okay, so it can even be more than 12 months. It can be in a period of up to 2 years. Okay, so again, depending upon what is the requirement, it can be done. Okay, so now we will look at life cycle test. So basically, a life cycle test is nothing but determining the loss in performance or loss in capacity after the cell faces continuous charging and discharging. So in the previous test, we had seen that the cell, how it would lose performance if it were to be isolated and disconnected from all load. Okay, but here the test is to see how it would perform if you were to continuously connect it to a load and continuously charge it and discharge it. Okay, for a minimum period of 14 days. Okay, so once again, we see here as per ISO standards. So the battery is first and foremost kept at 25 degrees Celsius, and then it is subjected to something called as a cycling process. Okay, so cycling process where you will charge the cell till it reaches 80% and then discharge the cell till it reaches 30% of its capacity. Okay, so this charging and discharging continuously happens till 22 hours of this cycle is complete. Then once again, 2 hours is 2 hours rest period is given, and then once again for the remaining 22 hours, the same cycle is repeated. Okay, so the same thing, this goes on and on till 7 days is completed. The test period of 7 days is completed, right? So once 7 days is completed, once again a pulse power characterization test is carried out to see if there is any change in resistance. Okay, so as I had mentioned earlier, as the number of cycles goes on increasing, so you can perform the pulse power characterization to see what is the change in resistance. Okay, and then the same cycling is once again carried out for another 7 days. Okay, then at the end of the 14 days, we will see that there is a static capacity test. Okay, so static capacity test is to see capacity loss. Okay, so this capacity loss will be once again be taken with relative to the initial capacity loss, initial capacity of the cell. Okay, so at the beginning of this test, one static capacity test is performed. Okay, and once the 14 days test period is complete, once again a static capacity test is performed, and with relative to the original capacity, you will be able to determine your capacity loss. Okay, so this is your complete cycle test, your life cycle test. Okay, so that is with respect to all of the tests that are to be performed, right? So here at Decibels Lab, we are currently using this equipment here supplied by a battery testing manufacturer called Newware. Okay, so the device model is called BTS 4000. BTS stands for battery testing system, and basically it's an 8-channel instrument, so you can test up to 8 individual cells of different capacities, of different specifications. Okay, and it can supply a maximum of 6 amps and limit itself to 5 volts. So it's basically a low power testing machine, and there are other variants as well to this. So there is also a 5 volts 20 amps. So there is a 5 volts 100 amps. There is also a 5 volts 1000 amps. Okay, so you can find the complete list and configuration of all of these machines on newware.com. So for those whoever is interested, you can head over to this website. You will be able to see a lot of different machines offered by them. Every kind of test is performed, including drive cycle tests, reverse drive cycle test, your extremely high current rate test, your life cycle test, aging test, impedance spectroscopy. All of these kind of tests can be performed. Okay, so this is an introduction to what we use here at Decibels Lab. And currently, as we speak, life cycle tests are happening to a bunch of 18650 lithium ion cells. Okay, so we're trying to see up to a cyclic limit of 500 cycles, what will the cell behavior be? Okay, so that is our current objective here at Decibels Lab. Okay, so here are also some other instruments and some other companies that use different kinds of testing machines. So here at Ether Laboratory, the same similar kind of machine is used from Newware, but here it will be used in bulk quantities. So here more than 5,000, 6,000 cells are tested at once. Okay, and here these two are temperature chambers. Okay, so these two are temperature chambers. Okay, and it can also simulate humidity. Okay, so here on from Tesla, they use Arbin, and this is actually one of the world's most widely used testing bench. So it can perform testing on all kinds of cells, so starting from coin cells, heading over to pouch cells, heading even prismatic cells. It can even they can even test they say they can even test like other types of other types of cell formats. It has a complete variety and a very huge range of testing capability, including like submersion test, underwater test, high altitude, low altitude test, inverting the battery, testing the battery by inverting it, testing the battery by damaging it. All this is possible using Arbin. Yeah, so not only Tesla, but even Scania, Volvo, Mercedes Benz, yeah, all of these leading manufacturers, they rely on Arbin for their battery testing. Yeah, and SignLab, this particular company is basically they're open, they're global market. They supply to the global market, so it's not just restricted to EVs. It's it even goes to power plants or household sort of appliances. Power, things like factories, all of these. So these are the different testing facilities that you can see commonly used in today's market. Yeah. So this is how a test schedule would look like if you were to utilize the Newware software. Okay. So here a simple static capacity test is done. So here you can see, you can mention the time for the test. You can even mention what current limitation you want, what voltage limitation you want, what capacity limitation you want, and how many for how many seconds do you want to record the data. So all this you can mention, right? And this is what is called as a step manager. Okay, so step manager, and this step manager actually helps you to give whatever kind of test it is you want. So this really has not that much of a limitation, except for drive cycle. You can basically perform all other types of tests in this. Okay, so that is with respect to our machine and the Newware software. And here, as I had mentioned earlier, so some of the testing standards. So all this throughout the entire webinar, we have seen ISO standards, but there are also IEC standards, SAE standards, which is very widely followed in case of automotive applications. So UL is basically towards household, electrochemistry, and also towards some amount of automotive. US Department of Energy, and ELICERT. Okay. So there is also another standard called as AIT, Austrian Institute of Technologies. They have also introduced their own standards for European electric vehicles. So there are many manufacturers in Europe that follow Austrian Institute of Technology as well. Okay. So these are the several different standards, and there are the identifying numbers. So these are the latest numbers. Okay. So recently, US Department of Energy has released their 2019 manual, but currently it is not accessible. Okay. So yeah, with that, we have come to the end of today's webinar. So that is your complete overview of cell testing and cell characterization. So now for the future scope, basically, what is the future scope? So after you have obtained all of this data, you can create a basic mathematical model of a cell in a software. You can then utilize this data to simulate the cell in different environments, especially when you're trying to design an electric vehicle. It would be very, very expensive for you to test the vehicle multiple times, do multiple tests on the hardware on the test bench again and again, right? So which is why you would have to perform software simulations to a certain extent. So this data can be utilized in such models. You can expose the model to different situations, different environments, and see how the battery pack responds. And then also you can develop things such as algorithms. Okay, so there are things like state of health and state of charge, state of power, estimation algorithms. Okay, so all of this the data that you have been obtained from the pulse power characterization, from the life cycle test, from the thermal abuse test, from the shock test, from all of them, this data can be completely obtained, and it can be tailored, and estimation algorithms can be developed so that batteries can be further developed and can be improved much and more in the future. Okay, so with that, we come to the end of this session, and now we will have a short Q&A session. So whoever has any questions can go ahead and type it up in the chat box.